So that's what nuclear fission is. You have come across it before. Fission, the important thing to remember is fission is the splitting up of atoms, okay, and a very small amount of fuel causes a huge amount of energy, which is really good for us. But as I said, because of this chain reaction, because every time it splits, a neutron is fired out again and could cause another splitting, we want to be able to control it. And the next page is all about how we control it. So in a nuclear power station, obviously in a nuclear bomb you don't want to control it, but in a nuclear power station you don't want it to explode. So the fission reaction must be controlled, and this allows the energy to be released steadily. So only one neutron from each fission reaction must be allowed to go on to cause another fission. So you can see some of them give out more than one neutron. So we want to limit the amount of neutrons that hit other atoms. The central part of the nuclear power station is the nuclear reactor. And the reactor contains uranium fuel in long canisters called fuel rods. So they're just big, long rods. Okay. The reactor also contains control rods, so they're quite important. These are made of material that absorbs neutrons, so they can limit the amount of neutrons that are in play. Okay, so they can limit the amount of splitting of atoms that happen. Boron is a material that's quite often used for those control rods. And we can decide how many neutrons are firing about, because these control rods can be lowered or lifted out of the fuel depending on how fast you want it to happen. So if you want more neutrons firing and more nucleus splitting, you lower them into it. But if you want fewer neutrons moving around, you rise them up. Sorry, other way around. If you want fewer neutrons, you lower them in, so they absorb more. If you want more neutrons, you rise them up, so they don't absorb as many. Okay. So the control rods can be moved in or out of the reactor core. When they're rising, they absorb lots of neutrons, and the chain reaction is stopped. When they're pulled out, fewer neutrons are absorbed, and more neutrons are used to cause fission, and therefore more energy is released. Okay, so you've got control rods, which are an important part to control the neutrons. You've also got something called a moderator. Okay. In a fission reaction, it works better if the neutrons are slightly slower than they would be normally. So a moderator is used to slow down the neutrons, because slow neutrons are more likely to cause the fission of a uranium nucleus. And light atoms, such as graphite, are used as moderators. Okay. Don't worry too much about this diagram. All it is it's showing that we want a slow neutron to hit a uranium, which splits up, and when they split up, they fire out fast neutrons. So we want to slow them down. So we want them to be basically passing through the moderators again and slow them down. Some of them get absorbed, so that they don't cause another fission reaction, and some of them go on to cause a fission reaction. Okay, and again, they fire out fast neutrons. We want them to slow down, so they go through a moderator to slow them down. Some of them get absorbed, and some of them go on and cause another fission reaction. And the other main part of the nuclear reactor is the coolant, which has to be circulated around the reactor to cool it, basically, to remove the energy released by the chain reaction, and the containment vessel to absorb the radiation released in the reactor and shield the surrounding environments, because you don't want the surrounding environment to get radiated and you don't want it to get too hot. In most nuclear power stations, carbon dioxide gas is used as a coolant, and several meters of concrete is used to shield the reactor. Okay, so there you have another diagram here. So the cold gas cools it down. We've got uranium rods, which are the fuel. We've got absorbing rods, so we've got the control rods that can move in and out, depending on how fast we want the reaction. And we've also got the moderator that slows them down. And there are a number of advantages and disadvantages of nuclear power. Obviously, they don't cause global warming. We don't get carbon dioxide gas given out, but they do produce toxic waste. Okay, very small amounts, but there are still toxic waste. So, advantages: nuclear power stations are relatively clean. They don't release gases like carbon dioxide, which causes the greenhouse effect and global warming, or sulfur dioxide, which causes acid rain. The amount of ionizing radiation released into the environment is small, compared to the background radiation. A large amount of energy is released from a small mass of fuel, and the quantity of waste produced is relatively small compared to the tons of ash produced by coal-burning power stations. The disadvantage is they produce radioactive waste that stays radioactive for thousands of years, and they have to be stored safely. Small discharges of certain radioactive materials may be responsible for causing certain types of cancer. We're not sure about that. Human error, such as at Chernobyl, if anyone's watched the Chernobyl TV show, it's really, really good, I recommend it, may release large amounts of radioactive materials into the environment. But don't watch it if you're squeamish, by the way. Nuclear power stations are expensive to decommission because the reactor core will remain radioactive long after its use. So we're going to look at those questions in a second, but that's nuclear fission. The other type of nuclear power that we could potentially use in the future is nuclear fusion. So fission is splitting up of atoms. Fusion is fusing them together. Okay. So fusion occurs when two or more atomic nuclei collide at very high speed and join to form a new type of atomic nucleus. So they form a slightly bigger one. Okay. This is basically what happens in the sun, but the conditions required to do this are quite difficult to achieve. So you have to have really high temperatures, you have to have really high pressures. So it's actually quite difficult to get those conditions. And that's why we don't really use it at the moment, because we don't really have the ability to get those conditions and sustain them for a long time. People have done fusion, people have had created fusion, but it doesn't last long enough to really be a sustainable power source yet. But it probably is going to be used in the future, because it is. There's pretty much hardly any disadvantages to it apart from not being able to do it yet. So what happens is it's basically different isotopes of hydrogen. So basically hydrogen, but with different amounts of neutrons in them. Okay, and they squish together and they fuse and they form helium and a neutron. Okay, now these two things that we use to create fusion can be found in water, can be found in the air, so they're safe. And then it forms helium, which is just a natural gas. Well, not natural gas, but it's naturally occurring, okay, so it's not dangerous either. So both what we use and what is made is not dangerous. And there's plenty of it around. It's not rare. Okay, so actually, if we could do this, it would be brilliant, because it produces loads and loads of energy. The products are safe. We can get loads of the stuff that we need to make it. But the only issue is we need those conditions to be able to actually do it, which there are people researching at the moment. So hopefully at some point soon. So large quantities of energy can be released only if millions of nuclei are fused at once. The sun releases its energy through vast numbers of hydrogen nuclei fusing into helium every second. And to produce fusion, the atomic nuclei are forced together at very high temperatures and pressures, and reproducing these conditions is extremely challenging. And JET, the Joint European Torus, is a working nuclear fusion reactor in Oxfordshire. So we can do fusion, but it can't last for very long. And that's the issue with it. But ideally, that will be sort of the power of the future. Okay. So, what I'm going to get you to do is I'm going to get you to go back. I know we did comprehension last time. There's only 3 questions. I want you to answer those questions on page 25. The answers are all in the previous couple of pages. So start with that, and then we'll probably do a little bit of research. Okay. So start on those questions.